There is a road that has been standing for over 2,000 years. It has carried armies. It has carried empires. It has endured floods, freezes, and the full weight of centuries, and it has never been repaved. Not once. While modern highways crack within 5 years of construction, while entire cities budget billions annually for pothole repairs, while commuters lose axles and alignment to roads that were built last decade, this ancient road continues to function. We are talking about the Roman road network, over 80,000 miles of engineered surface laid down by an empire that collapsed over 1,500 years ago, and portions of it, the original stone, the original subbase, the original drainage system, are still intact today. So ask yourself the question that the asphalt industry does not want you asking. If roads can be built to last 2,000 years, why are ours designed to fail in 5? That is not incompetence. That is a business model. Let us begin with what the Romans actually built. The Via Appia, the Appian Way, was constructed beginning in 312 BC. That is over 2,300 years ago. It connected Rome to Brindisi, stretching over 350 miles through the Italian peninsula. Generals marched on it, trade flowed across it, and it's self-maintained. Not through magic. Through engineering so precise and so structurally intelligent that the road managed its own degradation, shedding water, redistributing load, and resisting deformation through the geometry of its own construction. A Roman road was not a surface, it was a system. The Romans called the layered construction method the agger. It consisted of 4 distinct strata. The first layer, the statumen, was a bed of large, flat stones set directly into prepared earth, often 12 to 18 inches thick. Above that came the rudus, a layer of broken stones and rubble bound with lime mortar. Then the nucleus, a finer mixture of gravel, sand, and lime cement, essentially ancient concrete. And finally, the summa crusta, the top surface, fitted with large polygonal basalt stones, cut and shaped to interlock with extraordinary precision. No gaps, no seams, no place for water to enter and destroy from within. This is the mechanism of self-repair that has been erased from modern engineering education. The polygonal stone surface was designed so that individual stones could shift fractionally under load without compromising the overall structure. When a stone settled unevenly, surrounding stones redistributed the stress. The geometry did the work. No asphalt overlay, no resurfacing crew, no contract renewal. Every Roman road was also crowned, built higher at the center than at the edges, so that rainwater drained laterally into stone-lined channels called fossae, running alongside the surface. Water was the enemy. The Romans designed every inch to expel it immediately. Now compare that to asphalt. Asphalt is a petroleum byproduct, a flexible binder that holds aggregate together. It softens in summer heat and fractures in winter freeze. Every crack becomes a channel for water infiltration. Every infiltration begins a cycle of freeze, expansion, and surface failure. The road does not shed water. It absorbs it. The Romans knew this. The Persians knew this. The Persian Royal Road, stretching over 1,500 miles from Sardis to Susa, used dry-laid stone and compacted gravel subbases engineered for water expulsion and load distribution. The Inca road system covered over 25,000 miles across the Andes, using fitted stone slab surfaces on mountain passes with no mortar, no bitumen, geometric precision, and gravity holding everything together. Independent civilizations on opposite sides of the world arrived at the same conclusions. This was not coincidence. This was correct engineering. So when did we abandon it? And more importantly, why? Here is where the investigation turns. In the late 19th century, something shifted in road construction philosophy. It did not shift because engineers discovered a better method. It shifted because a new industry had a product it needed to sell. The petroleum industry had a problem. Crude oil refining, exploding across the United States and Europe in the 1880s and 1890s, produced a heavy viscous residue after lighter fuels were extracted. This residue was called bitumen. It was cheap. It was abundant. And for years, refineries had no profitable use for it. That changed when road engineers began experimenting with bitumen-bound aggregate as a surface material. Early asphalt roads were marketed as smooth, quiet, and fast to install. They were also fast to degrade, but that detail was not featured in the promotional materials. The connection between the petroleum industry and the infrastructure decisions of Western governments in the early 20th century is not a theory. It is documented history. Standard Oil and its successor companies had direct financial interests in seeing petroleum-based road surfaces become the global standard. The lobbying apparatus deployed into municipal and federal government was formidable. By the 1920s, asphalt was not merely a road surface, it was policy. Building codes across American and European cities standardized around asphalt and concrete. The institutional knowledge of stone road engineering, the quarrying techniques, the geometric fitting of polygonal sets, the drainage calculation, began disappearing from engineering curricula. Not because it was disproven, because it was not profitable. A road built to last 2,000 years is a road that cannot be repaved. A road that cannot be repaved is a contract that cannot be renewed. And a government that owns roads requiring no maintenance is a government that cannot be billed. There is the motive. The asphalt paving market today is valued at over $300 billion. Globally, the United States alone spends over $100 billion annually on road maintenance. Every pothole filled with hot mix asphalt will need to be filled again within 2 to 5 years. That is not a repair cycle. That is a subscription. Some will argue that asphalt is faster to install, that modern traffic volumes are incompatible with stone surfaces. These arguments deserve examination, but they must be examined alongside the question of who funded the research that established them. Because when you follow the money in 20th century road engineering, you find petroleum interests at nearly every significant policy junction. That is not coincidence. That is influence. The principle is so rational, it should be taught in primary school. The fact that it is not, the fact that it has been quietly removed from mainstream civil engineering training, is itself worth investigating. Here is the physics. A road fails in one of two ways. The surface material degrades under mechanical stress, or the subbase loses structural integrity through water infiltration and freeze-thaw cycling. Asphalt addresses neither failure mode permanently. The Roman system addressed both at the design stage. The statumen, the base layer of large flat stones, was a load distribution platform. When a heavy wagon passed over the surface, force was transmitted downward and spread laterally across the entire statumen. No single point in the earth below received concentrated load. The road did not sink, it did not rut, and the drainage system ensured that water never reached the statumen in the first place. Water that cannot infiltrate cannot freeze. Water that cannot freeze cannot expand. A subbase that is never saturated never fails. There is also the material science. Basalt has a thermal expansion coefficient of approximately 5 to 7 microstrains per degree Celsius. Asphalt has a thermal expansion coefficient of approximately 15 to 25 microstrains per degree Celsius, 3 to 5 times greater. In a city like Chicago, where temperature differential between winter and summer exceeds 100 degrees Fahrenheit, an asphalt street expands and contracts by the equivalent of several inches across a city block every year. The road is thermally tearing itself apart. Roman roads in climates as extreme as Chicago's survived because basalt does not move. Geometry does not fatigue. Now, the suppression mechanism. In 2004, the Dutch research institution Deltares published a comparative infrastructure longevity study examining historical road surfaces across 12 European countries. Their findings, which received remarkably little mainstream press coverage, indicated that pre-industrial stone road surfaces outperformed modern asphalt surfaces in structural longevity by a factor of between 15 and 40, depending on climate and traffic load. 15 to 40 times more durable, using materials requiring no petroleum, refining, generating no toxic runoff. In 2011, the city of Ferrara, Italy, restored a section of medieval stone-set paving using documented Roman drainage specifications. As of 2023, that section has required zero maintenance interventions. The surrounding asphalt streets in the same district have been resurfaced twice in the same period. Engineers in the field who have attempted to introduce stone paving specifications into municipal bidding processes encounter a procurement system so thoroughly standardized around asphalt that alternative materials cannot be practically proposed. The administrative forms do not have fields for basalt. The cost calculators do not account for 2,000-year service life. That calibration did not happen accidentally. The archive does not lie. 2,000 years of evidence is sitting in the ground across Europe, the Middle East, and South Asia. It is carrying foot traffic in Italian hill towns. It has been analyzed, measured, and documented by engineers who understand exactly what they are seeing. A road built correctly does not need to be rebuilt. A road that does not need to be rebuilt cannot generate a maintenance contract. And an infrastructure model that generates no maintenance contracts is an infrastructure model that the industry will ensure no government ever adopts. The knowledge was never lost. It was removed. We are the ones who put it back.